Thank you. Thank you. Great to be here. Small models are all we need. Pretty bold claim, right? So let me try to show you where it holds in practice. So my name is Robert. I work at Bencha International. We build AI-powered data infrastructure for the second-hand fashion market. Today we process around 250,000 product listings a day, more than 1 million images on a daily basis from various second-hand marketplaces. And from each product listing, we extract product attributes, then we turn into pricing intelligence and other downstream signals. Today, I walk you through how we use knowledge distillation to replace a proprietary model API calls with small self-hosted models. I would say that the approach is more interesting than our use case, as it applies anywhere where you have a narrow, well-defined task and you're calling a large model thousands of times. So before our case study, let me frame the broader argument. So there are 3 reasons to bet on small, task-specific models. First, they're powerful enough. So for narrow, well-defined tasks, we can fine-tune small models, and they can match or even outperform frontier models. And the gap is shrinking with every model generation. And second, they're operationally superior. So we get fast inference and fast training on commodity hardware. No API dependency, no rate limits, no vendor lock-in. You get full control of the data and deployment and the model. And that matters when you're running a production system at scale. The last one here is orders of magnitude cheaper. We can run self-hosted small models around 10 to maybe more than 100 times cheaper than calling proprietary model APIs at scale. And the savings compound with volume. So the more you run, the wider the gap gets. I think there's still a lack of popular awareness when it comes to small models in general. They don't receive the level of attention as LLMs, despite often being a better fit for many production cases. I would say that these 3 properties reinforce each other. And for us, I'll go as far as to say that powerful enough means that we can use them. Operationally superior means that we should use them. And orders of magnitude cheaper means that we must use them. And I'll show you why. So as I said, we process 250,000 product listings every day. At our production scale, there are 3 walls that we hit when we try to work with this with proprietary model APIs. The first one is latency. So the API round trip takes around 1.5 to 10 seconds. So if the user wants fast response, the API can't deliver it reliably. And then the second one is cost. API cost scales linearly with volume, which in our case would mean that we would spend more than $247,000 on our batch inference alone for a single service. For a startup, that's a significant line item. And then the third batch here, reliability. Rate limits cap your throughput. The provider can change the model without warning. Your data leaves your infrastructure. You basically build a pipeline around an endpoint or endpoints that you don't control. And the reflex answer, just use an API or just use GPT, works fine for prototyping. At our volume, with our latency and throughput requirements, it breaks. So before I explain how, let me show you the results. So we trained 2 different models, one sub 1 billion and one sub 2 billion parameter model, and achieved near frontier accuracy. We got roughly around 85 and 91% with the frontier model. And this is from the first iteration on a single GPU, I would say. And these numbers are increasing with every cycle. And now for the model here on the right-hand side, the API round trip now takes 1 to 2 seconds instead of 1.5 to 10 seconds. So let me be specific about what our model does exactly. So we use vision language models to do structured output prediction. So we take a different number of product images as input and then produces a structured JSON object as output. That includes 20 types attribute fields like category, color, material, brand, and so on. And then we have 2 deployment contexts, one user-facing where latency matters most, and one batch pipeline from our scraping side where throughput matters most. And today, the same model weights serve both, but with different optimization priorities. And for us, latency is a root constraint, and everything else cascades from it. So if we make faster inference on a single GPU, we get higher throughput per GPU and lower cost and resource footprint per listing. What we knew up front was that our users, they won't wait more than a few seconds. Our throughput targets, they crystallized as we understood our scraping volume. And the cost became a deciding factor once we realized what the bill would be at scale. And then resource footprint, single GPU per instance, means that we have a small, the model is small enough and fast enough to run on a single GPU. And then for production, we can scale horizontally, but the economics work because each instance is cheap. And as we see, every constraint points to the same direction. That is that we should use the smallest model that solves the task. So the distillation pipeline. First, we wanted to test feasibility of the task at hand. So we tried 2 open weight models selected for latency, mobile, and single GPU fit. We tried them on zero-shot prompting for 7 selected attributes and found out that they weren't production ready. So we tried a frontier model that turned out to be very capable. It was even more correct than our scraped ground truth, actually. So we decided to expand to 20 attributes. It was too expensive and too slow for production, but that told us 2 things. The task was feasible, and the frontier model was powerful enough to become our teacher. So for $3, we generated our training data with the frontier model across our image dataset. And then, since we're working on a structured extraction task, we need a well-defined ontology, meaning the set of valid values for each attribute. And in our case, this step is critical as ambiguity in the ontology will become noise that the student inherits. There are a few ways to go about this. What we did was that we derived the ontology empirically by analyzing the teacher's prediction distribution, so collapsing edge cases and mapping equivalent values to canonical forms. So our ontology is actually defined by what the teacher predicts, not by any design docs or any assumptions. In effect, our student also becomes more consistent than a teacher. And as noted here on the slide, an escalation principle runs through all of this, as we always try the cheapest and the simplest approach first. So our pipeline gives us a model, but what makes our distillation actually work is the quality of our training data and the iteration loop. So there are 3 properties of good distilled data: accurate, diverse, and consistent. So we first needed to validate our teacher outputs. Most of the attributes were reliable as is, while others needed more careful review. So we started with thorough visual inspection and then validated iteratively as our pipeline matured. And then the data set should match, that we train on should match the production distribution, meaning that we should train and prepare the model for what it's going to be used for. So if we have 30% blurry phone photos in training, we need that in production as well. And here we also need to consider edge cases that are critical for the business. And the last batch here, the data needs to be consistent, so we need clear values for the ontology in order for the model to be consistent. For instance, what's dark blue versus navy? And as I mentioned before, we resolve those into canonical forms, so the students end up being more consistent. And then we have the distillation loop, similar to the typical machine learning training loop, to be honest. After training, we evaluate per attribute, we do error analysis, we see what works, where and why the model fails, and based on our findings, we refine the data and the ontology and retrain. And each iteration raises the ceiling. And then the 80-20 principle applies here, so we always try to fix try to find where we can move the needle the most, which in our case has been fixing the worst attributes first. So now that we built the model, let me talk about some serving considerations for our sub 2 billion model. So every modern serving stack supports continuous batching as some form of paged KV cache memory management by default in order to maximize concurrent requests. Continuous batching means that we don't wait for the slowest request in a batch to finish. Instead, new requests can fill slots once they open up. And page KV cache memory management makes this work at scale by allocating KV memory on demand for each request instead of pre-allocating for the worst case. KV cache quantization compresses the KV cache. This basically frees up virtual memory. This enables us to handle longer context or more concurrent requests. In our case, we tend to be compute bound rather than memory bound. So this optimization only helps once we hit memory limits first. And then chunked prefill splits the prefill into smaller chunks and interleaves them with the code steps from other requests. This helps keep tail latency predictable under load, which is great for our user-facing API. For our batch jobs, we can run a high concurrency, so the extra scheduling overhead here actually reduces our throughput significantly. Prefix caching means that if every request starts with the same system prompt, we can compute KV cache once and then reuse that across requests. This is almost free latency savings. And for large models, you typically rely on speculative decoding, weight quantization, and tensor parallelism. Since our model fits comfortably into a single GPU in half precision, we can safely ignore these optimizations. So here we have it. These are example calculations from our batch processing. We have two scenarios, the proprietary model API and our self-hosted fine-tuned model. Assuming 250,000 listings a day, we are roughly around 113 times cheaper. No rate limits, no vendor lock-in, but full control. So we get 91% of the accuracy while being more than 100 times cheaper. And this is from the numbers are from the first iteration. So we're actively closing the accuracy gap through our distillation loop. By having better ontology, better data, and then we get better performance. Each cycle improves the model, while the economics stays roughly the same, until we are able to run an even smaller and even faster model, that is. So I've been working on second-hand fashion attribute extraction, but the knowledge distillation approach generalizes far beyond our use case. The core insight is that when you have a narrow, well-defined task, every repeated LLM call is a distillation opportunity. So if you're calling a frontier model the same way on a bounded task thousands of times, you have a training signal, and you can fine-tune a smaller model. So this applies to structured extraction, classification, routing, generation, and transformation. Basically anywhere where the same call repeats a scale, you can evaluate the output, and you have the output follows a learnable pattern. And lastly, and critically, agentic workflows. If you have a multi-step pipeline where each step make LLM calls, you can distill each step independently. So you don't have to distill the whole agent, just the repeated parts. The pattern is always the same. We observe what the frontier model does. We use the output as training data. We can fine-tune a small model and then replace. And then we can repeat at whatever scale makes sense. So today our model is deployed and we use confidence thresholding. So if the model is confident, we use a prediction. If not, it depends on the context. For our user-facing requests, we can fall back to the proprietary API of critical attributes. For our batch processing, we can flag the uncertain predictions, and then for the next iteration, we can sample from them. We can relabel them with a teacher, retrain, and then repeat. And once we have a model that we are confident in, we can run predictions on millions of items, and those predictions then become training data for even smaller models. So we can, our aim or ambition is to deploy on mobile devices as well. So the model that we ship today will generate the training data for the model that we ship next. Longer term, if a single model client can't close the gap on everything, we may specialize on route. For instance, OCR tasks separately from visual tasks. But we're not there yet, and we will only do so if the data tells us to. The key point is that the knowledge distillation pipeline is not a one-shot, so it's a loop that keeps running. Yeah, that was all I had for today. Thank you for listening.
Thank you so much, Robert. Super interesting presentation. And we actually have a lot of questions here from the audience. And we have a few minutes to ask you some of those, if that's fine for you. So the first one that I'm going to start off with is, can you explain a little bit more in detail how you use the frontier model or the teacher model to define the ontology for the smaller one?
Yeah, so we tested the different prompts with our images, and then sent them to an API. Could be GPT, could be Gemini, and so on. And based on that, we can analyze the distribution. We can compute the numbers and look at the distributions and see if we have some common colors or just obscure colors or categories that we can discard or keep.
Thank you. And what frontier models are you using? Like all the main different ones, or tell us a little bit more about that.
Yeah, we have tried a few ones, but I can't disclose which ones.
Right. And what is the final accuracy loss between the teacher model and your trained student, if you could touch upon that?
We're closing to 95%, but then it's more interesting to look at not the aggregate, but the individual attributes. So most of the attributes are basically solved, and now we're working on closing the gap on all of them. And obviously the hardest ones is extracting text. That's more difficult than seeing that this is a shirt or that this is white or whatever.
Right. Yeah. And then we have a question here from the audience. What's defined as a small model in your opinion or in your view? Like 8B, 30B, 90B parameters? What's considered a small model?
A small model?
View? Or in this case?
I would say smaller than 7B.
Yeah. Anything below?
Yeah, we are working with sub 1 billion and sub 2 billion. The idea is that the sub 1 billion should be deployed on mobile devices.
Right.
But then also, as I mentioned, we use vision language models. It could be that when we are able to generate millions of data points, we can train simple classifiers. But the future will tell.
Right. And then we have another question. Can these models be deployed on user devices to infer on the edge? And what kind of devices would that be? Like mobile phones or? Yeah,
it could be a mobile phone, Android and iOS. So that's the ambition.
Yeah. And then the final question here for you is, do you believe we'll see a general surge towards smaller models with frontier models getting a bit more expensive and small open source models like Gemma 4, for instance, and Qwen models getting better and better constantly?
Yeah, I think so. I think we're seeing just the latest months, just like Gemma and Qwen, they released powerful models. And I think as the hardware is getting better, Moore's law, and then also the models are getting better. So I think in the near future, users would expect. I think we should expect having the AI on our phones and not sending everything to the cloud.
Right. And lastly, like, what according to you is the biggest reason for why not more like companies are utilizing smaller specialized models to a bigger extent, as opposed to like these very large general ones? Do you think it's a lack of like understanding, or what do you think?
I don't know. Maybe it comes with the hype. Maybe, I don't know.
Yeah, like the bigger the better kind of
Yeah,
hype. Yeah.
it's easier to sell inside a company, I guess.
Right. Yeah. With that being said, we want to thank you so much and give him a warm applause. Thank you so much, Robert.
Thanks so much.
Thank you.
Thank you.